introduce myself. We have two things in our business. We develop customized software, and also we develop our own product, doubleware, and I will share about this product with you. When it comes to customized software, we have two areas of specialized in high productivity processing of the whole traffic. For the last 4 years, we've been developing high productivity web application firewall, which was mentioned by Gartner as a visionary firewall, and also we do with MariaDB. MariaDB, you can see us at three open source products. So MariaDB SQL system, it's one of major features of a release which we are going to enter. We didn't plan to develop our own HTTPS accelerator. So in fact, it's a hybrid of accelerator and a firewall designed to process a high volume of non-legitimate traffic. We started by developing a machine training module for identifying DDoS attacks. Then we wanted to integrate it into an HTTPS accelerator, and we found an issue. None of the existing accelerators was able to digest the big amount of traffic when it happens with DDoS attack. The contemporary HTTPS has some current, as we see it, issues. Number one, HTTPS is a global protocol. So in the global protocol, we have several currents, and then the amount of application is growing, and in the global network they use HTTPS, like Google Documents, a variety of applications. The more we have stages, the more each all installed above HTTPS. Social networks, social media where we can view a variety of videos, it is all HTTPS. So the internet communicates through HTTPS. So it was never viewed as a kernel protocol. But it is the protocol for the global network, and we must learn how to quickly process it. DDoS attacks at HTTPS level. So the most interesting things are happening at the application level. So contemporary floods are now mastered by us. We can cut them at a variety of hardware. It's not difficult. However, at application attacks, there is a variability, and a variety of loads can arrive to you. Asymmetric DDoS, as an example, where server spends much more resources than the client. You may have a big post request with a number of compressed parameters, and you may be asked to decompress it. The client may give you some garbage, and you will be decompress or compress it at the server side. It depends on the service, and also handshakes. Another example how a server may spend more resources than the client, and you may have many clients, limited resources. Another issue, number 3, a specific DDoS attack. When you have a big number of IP addresses, clients, every client sends you one request, one per minute, a small connection time, and you cannot get to this problem by the frequency analysis. So DDoS attacks are identified by the number of connections or by the total number of requests, and that's a problem. When you come across the issue, you have to have machine learning and identify such situations, and have to cluster your customers. I will come again to this machine learning because it's not a panacea. Then we will consider an example. A specific DDoS attack where port 80 was identified. Legitimate clients never would identify it. However, it was the case here, and therefore we needed to filter DDoS attack using this signature. It seems easy to filter, but there are issues. How to filter? That's the first question. There are several mechanisms how to filter. First, the most productive, it's a program firewall at the IP level, which using the errors can find you a pattern. And then the pattern will be worked, processed at the network card. HTTP, SDDF, a variety of things, how you can remove illegitimate traffic. There are two issues. If the line is too long, it may go beyond the package limit, and then this trick will no longer work because you cannot collect the stream. Packages may arrive at a different sequence, and we will miss this total signature. Therefore, in our DDoS block, we may have just one step to send, to divide our message into two packages, and then we bypass the filters. Then, if you look through headers, then host header follow the request header. U-value can be global, and we will find nothing. And then at DDoS bot, we may just give URI as smaller than the required number, and then we arrive at the edge, and we will manage to send our pattern. Another thing, we can filter at the HTTP accelerator, like Nginx, Contemporary Accelerator. They can do these filters. However, they are not designed to filter illegitimate traffic. But we have some good things. Suricata, for example, has an excellent set of rules at all 7 levels. You may tell me, like, filter this traffic from IP with host name $80. You may write application regulations for the IP level, for the application level. It will work, and it will filter. But there are some issues with IDS, like Suricata. They are not the terminal endpoint of the communication. It's just a piece which can cut traffic, but they are not communication points for CP or HTTP. And it originates several issues, giving the opportunity to bypass the tool. In the 90s, there were major research publications how to bypass the IDS system. The main idea is that your IDS has some TPIT stack. The target system can be built on a different basis. For example, Suricata is at Linux, and the target system at VD. So they collect traffic differently, in different ways. So you have a different way assembled streams, and this is a vulnerability. For example, overlapping sequence numbers, and whether the first or the second segment will be taken from the overlap. That's a question. Several stacks may have several operation procedures, giving the opportunity to bypass the system. Another issue, we do not participate in the communication, so the processing of the applied traffic is taken at our base. SSL just streams processed at the terminal point HTTP and at our hardware. And then we have our own filtering module, which will unfold SSL and does the necessary processing. We do it twice. We need SSL terminates the HTTP, and we need to duplicate the work. How to have DDoS protection? We are not preventing, we are mitigating DDoS attacks. So in a general case scenario, we cannot 100% filter the attack. DDoS attacks very often change their signatures. In course of time, they move between types. Bots can implement a variety of attacks, so we can't filter them 100% of the time. So some of parasite traffic arrives to the target system. So, and we want to protect, even pass the filtering system. So we want our protection system to allow us to go through stress conditions. So we want to befriend the two systems, the system level and the accelerators level. So our filtering system must be the terminal, the end communication point. We must quickly process the network traffic, have a powerful input-output system, HTTP processing, a flexible filtering system, and a fast web cache to mitigate DDoS attack, which will go through the filter. So I mentioned that there are some issues with the machine learning. Let me come back to it. When new traffic arrives to you, you have to first to understand the cause, whether it's just marketing campaign or you indeed got some DDoS attack arriving at you. So you have to pasteurize the traffic, to sort things out. And during the DDoS attack, while you are sorting out the traffic, you have a certain lag. A good system can identify the issue within 1 minute. A poor system will take longer, but it means there is a lag, which is a negative consequences. We want to avoid it. So it is good to have a web cache when you have a variety of requests you can digest by having this tool. Let us talk about the system class, which we call the application delivery controller. So as you see, it has many elements. We focus mostly on a very fast web cache, DDoS protection, and load balancer. There is another point, web application security. It's a separate tool. It is ensured by web application firewalls. We have some small components of WAF, but WAF component. But we never tried to be a true WAF, because a true WAF has heavy logic, sorting out SML, HTTP, ours doesn't do it. And there is a class of an occupied niche. We have a Web-accelerator with slow HTTP servers with some logic and possibly a database, and we must provide quickly traffic between the two servers, offload something to ourselves. The same idea is behind the WAF accelerator. If you have at the back end some slow WAFs and your applications are protected, it. So it is very, when there is a full set of signatures, so then this low is the speed. So we can separate it between several WAFs. We can do basic validation at the Tempest. We have offloaded the rules from these WAFs and to cut off the DDoS attack here. And we offload. So that's the description of our WAF accelerator. So why HTTP accelerators are no good for filtering? Because in our case, in Nginx, under certain conditions, at the extreme case, it can spend more time for filtering of illegitimate traffic than for processing legitimate. Here is an example. This is the base response message with the mistake, with an error, and we shall call the additional logic for the filtering module and see, and it's 1 extra microsecond. We must spend much less resources for illegitimate traffic compared for processing of legitimate traffic. Another thing very often used with these systems, like an ordinary HTTP accelerator, analyzers, log analyzers, looking through the frequency of requests from your client. But passing logs in today's world, not a good thing. When you have DDoS, it already slows things down. It's already slow. Everything is slowed down, your productivity is dropping, and access log is, in fact, one of the most stringent and limited productivity-wise points at HTTP accelerator. So your filtering tool must be tightly integrated with your work logic. That's the solution. Web accelerators, in general, well, let me make one step back. They are not bad, but they are designed for a different thing. They have their own filtering logic, not designed for filtering big traffic volumes. They were never designed for cutting off big traffic volumes. So we just distribute content through them, and contemporary HTTP accelerators have a variety, unlimited number of options for transforming your content, processing, giving it from cache, giving it from disks, etc. But filtering, it's a different thing. They were not designed for it. HTTP accelerators, which we well know, they were designed, developed 20 years ago, at the end of the 90s, early 2000. In their design, they were based on processing 10,000 connections, which is a very small figure by now. 100,000 connections, preferably virtual, of interest today.
The approach should be relevant. The systems should be different. And the next point, DDoS attack. Well, actually, there's a separate class of attacks. Web attacks, DDoS attacks, are cognition attacks, when everything is designed for a certain victim, determined victim. So if you can't process a big number of small packages, and your architecture is created for the a big number of small requests. If you can't hold a lot of SSL, then you won't be given that. If you have slow passes, you'll be given a big HTTP request with a big number of headings. So if the attacker thinks a little bit and considers your topic, he may choose the optimum attack. The responses that require most time from your system. And it's also interesting to review it because later we'll be talking about Linux kernel. And it's interesting to remember what systems we've had with HTTP processing. In the core, a while ago, Red Hat held TUX HTTP accelerator in its core. Then it was taken out. The problem with this approach is as follows. In principle, those were the same HTTP accelerators. They were made the same way, simply they were located inside the core. It has same flows, times, same thing. There was no copying. And then we received the send file, optimization of switching of context between the core and business space. And in general, we didn't need those kernel accelerators anymore. DDoS attack modified the situation since we want to get the maximum performance, and also SSL modified the situation quite in a big way, not regarding the attacks only. The problem with SSL is that if you have the website and you need to give the contact with via SSL, you need to take certain files from the disk, copy it in the user space. There you decipher it in a separate buffer, and then this buffer is transferred to the core for sending. So you have three copying: kernel user space buffer ciphering, and then again to the core. That's not great. Hence, the Red Hat and the Facebook already brought to the mainstream the TLS, and what worries the Facebook is that when we open it, we mainly it's open in we are coming to the Facebook not for the first time, so there are not many new users. So we have to do as soon as possible the secondary handshake to the seller, and then there's the big volume of traffic. So of importance is not the handshake at the new user, but the transfer of data in the stream. Well, let me tell you about this thing. Mellanox already has in the core, and I believe in the drivers, the probability of affording of TLS to the network card. So their cards do have the TLS. First, you do the handshake in business space, and then you give to the card the TLS for holding. And the next, last, the Netflix, it's also the core TLS, but it's interesting. Well, that's it. That's the way the modern TLS looks like. It appeared in the kernel 4.13. So if you get it, compile it with the own TLS, then you will have the kernel TLS. You may see the example of how it happens. That's a pseudocode. And the actual example is in this depository. That's what we do. First, there's the structure of data, which translates the context from the session, from the user space to the kernel space. We open the socket connection and create a new SSL session, and then there takes place the copying. That very copying from the beginning of the session. We get the value of the crypto context, the current one of CCL. Then we copy it into this new data structure, and then via the sysocopt, we first transfer all this. We transfer our current socket into the TLS condition. We connect it with the TLS, and then we copy the structure of the crypto context into the kernel. And we say that the socket via the constant TLS TX is ready for sending. So any data we record in the socket shall be deciphered, coded, and shall be sent via the connection in the coded way. Well, why for us why this realization is not suitable for us. The coded connection hash is great. You know, Facebook is not interested in the handshake. In our case, there's the SL DDoS attacks. There's plenty of those. It's a primary connection. It may be TLS renegotiation when you already have this session and the attacker is requesting you to regenerate the keys. So there's a big spectrum of attack, what you can do with the ZIL. That's why handshakes are important for us. Next, Facebook may say, now we're TLS 1.3. The browser and the modern Firefox has it. Well, but in general, TLS 1.3 is already here, and we can say that now we do it. The browser will enter via the new TLS. And the good thing about TLS 1.3 is a very good handshake. Well, we can't, because we always have legacy customers. Probably Windows XP is still alive, with God knows what TLS on board. And if we want to do the DDoS protection, we have to work with legacy customers as well. So legacy 1.2 shall be forever. We'll have to work with it quickly, and DDoS bots and TLS 1.2 will be coming. Hence, we have made our own kernel TLS. A bit later, I will tell you about it. So far, I'd like to tell you about why HTTPS accelerators are slow. And later, I'll talk about TLS. First of all, this tracing of HTTPL food for GNX. And GNX is already a mature project. It's well optimized, and the profile is pretty much okay. There's no hotspot that we now optimize and say improve efficiency by 20-30% or twofold. Any top from this profile shall give us several percent of optimization. The first in the top is HTTP parser. We have the copying in the user space. We have the challenger, system challenger, and send file. And resfa is the sending of input-output slow. And the last line is our limiting module, which added +1 microsecond for filtering. Well, in fact, if we see how many system challenges we call for processing of each request, not that little. System challenges are pretty cheap, but still they cost something. And just one system challenge may be removed, that's access walk. But in general, GNX without access walks is not great, and it's seldom done. Next, in the profile, on the first line, we saw the HTTP parser. And in modern HTTP accelerators is done in a very simple way. The only thing we can invent is to make a cycle of input data, to make a state machine with a case, and then to process the input data. We first process the current condition, then we jump onto this condition, and we process the incoming letter, current one, and then we do this. So we know that we need to switch to the next instruction, so we need to get to the end of our switch, then jump again to the beginning of the while, and then to do the switch again, and then to switch to the next instruction. That's the way it happens. In fact, we have the code generators, and they generate correctly. There's the right machine on the Vega, there's a special condition, and there's no inside the code, we enter where we need to jump. All this is converted in the assembler mark, so the transition takes place very quickly. Next, HTTP accelerators use mainly the web's functions for lines of processing in a good case. In a bad case, and it works slowly because they are very specific. First of all, we usually don't have the zero, terminating zero, but we have the terminating tokens. And server left, that's 2 bytes, not 1 byte. And we need to process, hence, both the 1 and 2 bytes delimiters. And when converting of lines takes place at HTTP case insensitive, hence in the code we keep the lines, we may decipher them in a certain register, and only do the ones that are at the input. So we don't have to bring it to the upper or lower register. We can do it at input lines. And it's not an optimum function. So we did our own lines, optimized for the modern processors. In most of the cases, the productivity grew, but not much, 1.52 times. And when we had big lines, big cooks, one may get like 6 times faster, up to 6 times faster. So the case curves were much better than the standard functions. The next, in the lines of processing of TPS lines, we have strict validation. We develop these algorithms for each set of alphabet. Right away, we process the probable. Hence, we protect ourselves from the attacks, from the injections. Input-output, if the package is coming on different kernels, then when the process begins to do one socket, the packages in the others may go down in the caches. Mind you, the HTTP accelerator is using rather heavy web cache processor. So caching on such systems in processes is not so good, and it may be optimized. Thus, these things we reviewed and redone. We've redone them. We've made our own fork kernel TV. Now it's simply a fork kernel MBTV. It's easy and fast to do it. It's simpler to do from the library to the kernel because it's a thing in itself than to bring the HTTP stack to user space. Well, that's the architecture of what we get. In general, we can say that this HTTP works on the same callbacks as SCP. So it's an and callback HTTP. Here it is filtered into the frame, and then the rules are generated on the IP level. Or there's the resending to the upstream, or it's taken from the cache. So it's like a normal stack, good stack. For the struggle against asymmetric DDoS, we use the quality service. So far, it's being developed. We'll get it later. And I'd like to say about the proxying of HTTP traffic. In general, when you get the package, It comes for a while, for a time term, and it's connected to a certain processor. And the control block, it's a small code, a small structure that describes the present condition of TCP. Then you copy it into a buffer. Then you should rewrite the HTTP header. Not talking about SL, you have to rewrite the headers, send them to the socket of the server, and one buffer is original. Then we transform into the other buffer, and then this buffer is transferred to the other kernel. Yes, if there's not one but 2 or 4 processors, then it slows down the general solution. Same with the caches, they feel bad. Next problem is that these HTTP control blocks should be synchronized. We have a duplex connection, and while we transfer the HTTP request to the server may respond to the previous request. So we have a duplex, and there's a problem of deadlock. So the server socket first is taken on that side, and then the customers is taken, and now it's into reverse way. Of course, we are programmers. We can solve it, but however, to take the walks built on different processes, that's not great. So we are using our own transport. There's the walk-free and buffer, and there's the sequence of the tasks for each processor. If we want to do something at this socket, at this processor, something happens, and we have to transfer to the other processor, to the other socket. Then we put this work into the read buffer. It's a very fast operation, much faster than the block. You simply write the pointer to the next cell. There's no conflict with the cache, and it works so that we only use the local pointers. So we have the transfer from one process to the other, but we have no synchronization on blocking and on the general data structure. So nobody is getting into somebody else's memory. The other problem is interesting problem is regarding the rewriting of HTTP headers. For example, we need to add a certain IP address, and usually we take and copy. We create the new HTTP message, we rewrite and redo everything. That's not great. So we do this way. We, in Linux, the socket SKB, the socket buffer, is on the pages, on the fragments. So we cut this fragment on the point where we have to insert. We add new data to the next fragment and rewrite the pointers at this. There's the chapter, the new data, and the tail. So we can modify the HTTP messages without any copying. And in the end, I'd like to consider a little bit the HTTP2. First of all, the protocol is rather special. It's good in general. It has a lot of different optimizations possible. But some optimizations for avoiding of copying do not work with HTTP. There's the compression, the cryptography, so there's more copying over there. Hence, the model is as follows. HTTP2 is good for working with customers because it's optimization for the global network. If you deploy HTTP between front-end and back-end, front-end and back-end, then it's better to optimize this than the HTTP2. Next is the quick. Quick is the HTTP2 is the optimization of the new. This is optimization on the level of TCP. So we get away the TCP and IP. We replace it with user space library. It's a kind of an analog as a using with ITP. There's a number of optimizations, cryptography. It works with a zero handshake, and we add a certain percent of duplication in case of losses. We use YouTube and Chrome, and we see it works well and quickly. With Quick, the problem is that this is UDP, and the administrators of it know very well that if it has opaque, and it's pretty much like UDP food, and it's a legitimate traffic. So it's a badly manageable protocol, not very convenient for filtering. And the last thing, we have TCP fast open, we have TLS 1.3, and if we talk about optimization, it may be not that interesting, because in general we already have the handshake. I'm about to finish. Well, as for the limits, we'll skip them. These are the options. In fact, I'd like to tell you that in general, the productivity is 1.8 million MPS on a small processor for kernel processor. If we compare our results with CSTON, therefore kernel 1 is here 1, 3, 2, 4, depending on how they measured. It's not a performance comparison. These are certain figures for the analysis. So the result is that in general the core peak is slow. If we do the traffic, the kernel stack is slow.
And then we need not only to cut the HTTP, but also have some clever modifications. We have some other narrow points and some interesting results with the cooperation of user stack. Kernel TCP IP stack is compatible with very good things like user tables. So if you left it to the user quick, you can do nothing with this traffic. So I'm done, more or less. Do you have any questions? Because my time is up. Thank you.
Any questions? People? We will hand you a microphone. Люди, мы вручим вам микрофоны для задавания вопросов.
At the beginning, you mentioned target attacks, DDoS, and you said if some points in your system are slow, so how would you see the ideal DDoS attack at the host-protected test? Well, we have some bottlenecks. Of course, we can't process TLS similarly to regular HTTPs, so we have certain limits. So at extreme cases, we can work better, but you can profile your application to find its bottlenecks. And if you use TMSS at the database, if you go to the index base and then to the database, and if the request to the database depends on the parameters, and then you generate the SQL request, then it slows things down. So you will just modify the parameter of requests. There is no, so to say, silver bullet. There are certain tools allowing you to work better. So you can, any system administrator may install a simple open source product and then have a DDoS protection and acceleration, everything which is needed. So without using building blocks and first put the accelerator and then go to network forums and file how to attach a variety of different elements. And if you have some complicated processes, then you may fail. So we want to have a commodity that any person may have. This is the base, and then construct the thing fast and easy.
Секунду.
Any other questions?
Уже почти. Прошу.
Alexander, my question to you is how you bypass the limits on the number of open sockets, I mean network connections. So you say 1 million connections. Well, there is no trick here. So we will just remove slow things like accept logs. We have no processing queues or receiving queues. When you look at the number of connections, so you look at IPF and you have speed locks at the network stacks, and we have none of them. So that's how we optimize our transportation between sockets, because every kernel we have their own set of sockets, and we will have this work in parallel. So we have linear upscaling. So you have several kernels working in parallel, and that's how we organize things.
Спасибо.
Thank you.
Еще вопрос?
Здравствуйте, спасибо за доклад.
Good morning. Thank you for your presentation. I have a pragmatic, so to say, question.
Расскажите, пожалуйста, как вы
Tell
эту
us,
технологию
please, how
продаете
you sell
клиентам, то
this
есть что
technology
им
to your
должны все это поставить,
clients.
свое ядро собрать,
So
или
it
что,
means
как вообще
they
это
have
происходит?
to put
Спасибо.
together their own kernel or what? Thank you for your question. So you can download all things and put things together yourself. Or we can give you a package. So we have the kernel for 9 and use Debian. So, but everything you can download and have the working technology. So we have the modified kernel, and we understand that professionals avoid to do it, especially when it's a heavy kernel. But we have the option working virtually, so we are faster at least 3 times than a regular HTTP accelerator. So you can use the mirror to virtuals, and you have a better option than a regular accelerator.
Спасибо. Еще у нас 2 вопроса. Давайте начнем с
2 more questions I see
того, кто
coming.
быстрее успел, с того и начнем.
Good morning. Your performance analysis, you have the web slide on that. Can you explain the testing methodology, whether we can repeat it at our end, because we have our own results? So let me explain you the technology. It's in detail described at this address. So the scripts, the servers, the generation process. So you go to this web link and you can repeat it at your end. So, and if you fail, please write to us. We will develop better our weeks and
One more question.
give you the answer. My name is Alexander. The next question. I'm representing the company hosting provider. So DDoS attacks are ordinary issues, and our protection is similar to yours. But I noticed that in 90% of all attack cases, they can either fail your server or fail your channel. So Tempests are done for a specific thing. We have 1 gigabyte input. In fact, there are several points, but each has 10 gigabit. And we repel almost all of the attacks. And if we can't, then the task is transferred to the cloak foil. So we work with our client. So your protection, what is the designed throughput? Because servers are not connected at 10 gigabits, usually 1 gigabit max. Let me answer you this way. So Tempest is used for any round foil. We do not protect the throughput of the canal because we work on top of it. We work at HTTP DDoS. About gigabits, I would not talk about the applied DDoS attack in gigabits. It's better base our conversation on transactions. And transactions are different. For example, you may distribute every request via clusters and then do some manipulation. When you talk about 1 gigabit, in fact, your gigabit can be very heavy in terms of processing. And HTTPS allows you to have the input of 110 gigabit and then work it at the server at simple transactions. At heavy transactions, you have to do some complicated analytics to still use the capacity of 1 gigabit. Let me rephrase my questions and let's say the server has X number of gigabits arriving to the server. Can repel it, but if we get it out of cache and a big amount, let's say close to 1 megabyte, 1 kilobyte, for 100,000 connects, and then it uses the entire put-through of the channel. Tempesta, I haven't seen a slide that would say that 1 kilobyte was given out for 1 million connects. How do you deal with this? We understand that you remove it from cache, but it's better to cut these connects. Let us take the extreme case. You have HT flood. You may leave it as it is without cutting it, but if you are limited in channels, you cut it. I missed this slide. By the way, we have it. We have an inbuilt tool to fight against this. For example, rate limits, a variety of connections using new and parallel handshakes, and we work on optimizing TOS. We have HTTP limits. So these are very under concentrated development at the moment. We have cookies and modification of cookies. We can give you a cookie challenge, and we do some task on JavaScript challenge at the moment, so we know how to cut the traffic. And one of the major differences between Tempesta and other solutions, for example, with the ban. So Tempesta, wherever there is a limit, whatever there is a challenge, you don't continue cutting it to HTTP logins. You put this level lower at the IP level, and you start cutting at the IP logging level, not at the HTTP level. Let us thank the presenter.
Напоминаю, что сейчас у нас по программе